As mentioned, I present some e-commerce use case, and it's about our way of our experience and our optimizations while we're following our way to link data, for using linked data in the e-commerce vertical. So for me, I'm head of research development at Unister, so that's a department of Unister targeting new technologies and try to make it available. Unister by itself, I'm quite sure that no one who has not heard my talk in London will be aware of what Unister is. Unister, it's an e-commerce company, was founded in 2002 in Germany. It's one of the major B2C e-commerce companies in Germany. We have many web portals, in particular in Germany, but also in Europe. These are hundreds of web portals and web services dedicated to travel, flights, travel packages, retail, news, and so on and so on. So many verticals. And we follow an integrated business model. That means that we would like to manage the technology by ourselves, to be capable of adapting new technology into our products and such, gain some progress and be first in the market, if possible. And that you have a number, we have 10 million unique users per month only in Germany. That's an independent measure, so it's not our count. And just to give an impression about the growth of Unister, in 2003 we had the first employee, and right now we have 1,600. So it's grown much. So about our use case, I cannot speak for all e-commerce companies, but I assume because of the many talks I give and the many discussions I have participated, that many e-commerce companies try to take advantage of big data and to try to unchain their data stores from the schema, because this is kind of a burden for our applications that we cannot take advantage of all the different information that's available of the web. And one of the main claims we have is to make the web our data store, data source for all the applications we have. So, but while doing this, we have some requirements to fulfill. That is, at least that it's a fast query engine, that's robust and scalable. And of course, we have heard it yesterday, we have quite the same situation. Of course, all our users want, the users want it now and want it all. So we have to be sure that it's ensured, that we get a good performance. So let's now look at the typical travel use case. Of course, it's just one vertical, but and it's strongly reduced. But you can see here that we, of course, have many times you have this kind of region tree. Oh no, that's not a tree, region graph, which shows some parent regions, sub-regions, and so on and so on. Then many hotels are most of the time available. The regions have several features, and of course the hotels also have many features. I can say most of the data sets available, considering hotels, have something around about 250 features that are annotated to hotel instances. So we have kind of an hierarchical region graph. We have hotels and regions with many features, and we have some typical queries, like select several features of a hotel. So that's very typical. You all will make something similar as you would like to travel to Barcelona, then of course you have picked a hotel. And query that might represent this process is shown here. Here we have something, we have selected a hotel. For this hotel we have selected 8 features. That might be explicit or implicit, both is possible. This hotel has to be in Europe, so that's not the query that's a non-selective query. And it has to be suitable for families, and we would like to have only 10. So that's very typical. And given this standard process or standard search query, we have derived 4 benchmark settings where we search for attributes of the hotel that might be, in the first case, very selective or less selective. We have simulated the situation if the user picks a region, if he sorts the results, and if he limits the selection down to a specific number. Most of the time we use 10. Our setting was just a subset of our available hotel data set. That's only 71,000 hotels. So you can see here that's not a big number. I can say the number of tuples is 16.1 million tuples. That's not so much. We used Virtuoso, and I can say, as I said, it's only a subset. While only considering hotels, we are looking on more than 680,000 to have all the worldwide worldwide available hotels represented. So we use Virtuoso in the version 7.1. That's the fast track available at GitHub. This data set materialized to 824 megabytes, so it's also not so much. And our experience always run 20 times, and we show the median here. So let's have a look at an example on all these example benchmarks, which conclude in this chart, And you see that by considering this, I would say, simple use case, we still have not the option to go on the level we would like to have. 2 seconds of query time is not acceptable for a web portal. You might know that you expect something more. You are all trained by Google to expect more. And of course, if you add some additional features, it increases up to 5 seconds over here. That's the worst case. But all the other cases also will decrease. So if we add some features which makes the overall query more selective, the runtime increases. So that's not okay. So
up to 10 features.
now that up to 8 features, and we add all the time something more like more located ins, more suitable fors, and so on. So it's only up to 8 features that's kind of suitable for most cases. So that's why we use this number. Okay, so our requirements for the industrial applicability, at least in e-commerce, are that we would like to replace the traditional database, but that's only possible if the Typo store is fast. So it shows a short response time. It is possible by a refinement to decrease the runtime. It has to be robust. So similar answer times have to be ensured. It has to be easy to scale up, and the system resources have to be used efficient. And that's not, while using this application, trying this application for the Virtuoso Typo store, it was not possible. So our requirements are not fulfilled. So we could say that that's it. We are not using Typo stores in e-commerce, but that's not our approach, at least not at research and development and at my company. So we tried something else. And we have looked at the data structures, and we see, of course, that there are many features available. And we just have looked at one specific point in the ontology where the hotels have, as I said, more than 250 features available. So we materialize these features connected to the hotel. So just this one was extracted. And it was extracted by representing it as a bit set, and you can think about it in this way. If you have this table showing all the hotels, showing all the parameters you would like to materialize, then you say what's valid, what's existing, what's not existing. Then you extract the bit set. That's the column. You extract them and store them somewhere. So that's nothing new. We all know that the column-based representation of data stores have a great impact on some queries. And but we have done something more. As we use only bit set, we have no index, so no extra data representation needed to access this bit set representation. It's very small. In particular, we have not compressed it here because it was not needed. It's so small that it fits in everything. It even fits in a Raspberry Pi. So we can do all the operations in memory. It's easy to update, and all inserts are also very easy. So that's the advantage of this data structure. And while applying this to Virtuoso, we have stored 16,000 properties within this bitset representation. We used Memcache for that. adds up to 63, around about 63 gigabyte. No. Oh no. I'm sorry. Byte, 63 megabyte. That I used, and the Virtuoso decreases in size from 824 to 706. So we have gained the progress there because this adds up to a lower number than that. And well, we adapted the buffer size to make it more complicated for Virtuosos. But just to show that that's not an advantage by itself. So. But now we have to make some use of this representation, and that was kind of difficult because we tried to integrate it into Virtuoso. And into Virtuoso, it's possible to integrate something with the plugin architecture, plugin interfaces. But we only achieved this, and I have to say, with the kind support of the OpenLink team, because they were very friendly and helpful, because otherwise we would not manage to integrate it. It was kind of difficult, and we also need some specific interfaces that are not available at the beginning. So that's something we cannot take the whole credit of. This was also supported by OpenLink, and it was supported by a GNO project, which is an EU project where we work together with OpenLink on making geospatial data available. Linking geospatial data to the linked Open Data Cloud. So, but now to the Virtuoso plugin. The Virtuoso plugin interprets some specific predicate the BIF contains. That's a workaround. That's something very, very ugly. I would not show the code for that. In the second step, we request the bitsets via from the memcache via JNI. JNI we use because we have already implemented a client for this bitset representation, so that's also a workaround. We compute the hotels using bitset operations on the address bitsets. That's a very natural operation, and it's very fast. And the fourth step, we map it back to hotel IDs via the Virtuoso we map it back to hotel IDs while using Virtuoso literal IDs. That's also a workaround and also very ugly. And finally, we get some cursor, some result set that we can push back to Virtuoso, and now the query can be answered. So you see, I would like to mention that all these things are not something like industry ready. They are just to prove that this approach helps to improve the performance. So let's have a look at the results. If we look at the first benchmark, we see that you just have to look at the blue lines and the red line and the green lines. We see that most of the time we are faster with the green line than the Virtuoso built-in functionality. That's true for the second test. That's also true for the second test. But we see, and that's a very important thing, that the more complex the query get, the less response time we have. And that's a very important thing for our use case. We see that's a stable response time, and we see that, so I would not like to hide that warm-up is needed to get the get the good performance. But I have to say that's not part of the bitset representation. It's not caused by the bitset representation. It's as we have to fetch all the literals back from the Virtuoso index interface, and that needs to be warmed up. Otherwise, it's not possible to make this in a fast way. So we see here that, as I said, more complex mean less response time. We see a stable response time, and so everything is fine if we consider this. On the second test, it's not quite the same. We see that if we have less selected features, then the Virtuoso part of the answering that is has the largest impact on the computation time, and that's why it's not possible to have such a great boost on the runtime. But you can see it's still stable, and that's also very important. And if we look at the third use case, while adding an order by to all the queries, we also see that it's possible to gain a lot of speed up, and we see here that it's very, very stable considering our representation. And the most important part there is that we currently don't understand something like sort by. So it is nothing we optimize via a bit set. We just compute the intermediate results so fast that sorting on the virtuoso side is quite easy. And the last use case where we limit the search results, we can see quite the same behavior, very fast response times. And that's something I would call industrial ready from a performance point of view. And but it's also not achieved by we have some knowledge about the limit. That's also done only within virtuoso, but because we have computer information very rapid. So, but you can see here that of course virtuoso takes advantage of the limit because it's quite hard, considering all these standard queries where just features are selected, because virtuoso is quite fast here. So, as I have just to compute the intermediate results, they can stop after 10 results and everything is fine. So that's something where we can compete, but not be much faster. But at the end, if you see that the less selected features come into account, then we see a large speed up. Okay, so finally, to summarize, we have proven that our implementation, considering bit sets, shows a good performance. The query time is robust. We are very resource efficient. We do not need a schema. In particular, it's not needed to move to a specific schema or something like that. But if you identify some specific entities having a lot of features, have a lot of properties that need to be represented, then it might be useful to use this representation. But you have not to change everything. That's very important because we would like to have still a schema-less representation. So, in conclusion, if you have something like a star pattern with many properties on specific entities, on specific classes, then you might use this bit set optimization and you gain a lot of performance. But as I said, our implementation is not production ready. There are many to-dos until this can go public. Of course, it can go public. I would not recommend to use it. We have to overcome the workarounds. We have to tighten the integration so that we know when something needs to be ordered and can represent this ordered result set. For example, we have to generalize the interface because we would like to extend even more different data stores that are available. For example, we would like to extend it to Elasticsearch, which is a very powerful cluster-based full-text search index, and this way make full-text search available within virtuoso, and we assume also increase the performance. So, yeah. So the takeaway messages: the e-commerce use case requires short and raw request times. While using bit set driven extension, we have proven that it's possible to achieve these requirements. And of course, right now we are capable of doing everything that it's possible in the traditional way. And I will have to make the next step and work actually schema-less to take advantage of the linked open data class. So, taking advantage of external data structures is possible. It's supported by virtuoso. We see it's a good boost for the performance. Thanks a lot.
Okay, thank you, Andreas. This was an interesting example of a very creative client that is doing a lot of extra work with the plugins. So, any questions?
Yeah, I just have one comment. Yeah. Hi. Okay. So the moral of the story that we see here is that genericity is the enemy of performance, and it's entirely appropriate to mix and match, let's say, the best of known data structures, and furthermore, so to get performance parity while keeping schemalessness, we will increasingly take advantage of regularity when it is present, in this case via bit sets. The integration with external full text indices is also like also on the text practices. It's an interesting thing, and also reducing the query planning complexity, which comes via these dedicated data structures, is an important factor. So all of these things together make this basically schemaless RDF an increasingly competitive technology. So this is a very, very nice example of all these trends coming into play, and more of the same sort of stuff is expected to occur in the future.
And I would like to add that we have here the advantage of working schemaless, and after we decided to have all the data represented, we can search for the performance flaws and then add additional data structures without changing everything. So that's very important for us because it's just an add-on to gain more performance.
Larry has a question?
Yes. So, although the use cases that LDBC is trying to represent are far from your use case, do you think that there would be ways to understand your problems within those use cases? Do you think that there could be a match between something which is far from the real use cases represented by LDBC and other use cases?
Well, I'm not aware of the details of all benchmarks, but I think the BI benchmark is close to the things we would like to have, because no, in this travel use case, of course, only because there are also many star patterns represented, and I assume that that might show similar behavior if we put our data, if we represent our data similar to this benchmark. So,
thank you. We can take one or two more questions, but I would want to invite the next speaker to connect her machine. So go ahead.
So thanks, Andreas, for the presentation. We've been working with a Dutch provider of travel services, and one of the things that was really difficult for them, besides the business intelligence, besides the recommendations, was to actually ingest new data and create, well, the equivalent of indices, right, for NoSQL databases. So they were looking at all sorts of cloud-based approaches, and we helped with that. What is your view on ingesting new data? Because hotel data changes quite rapidly.
yeah, of course. But the actual hotel data, for example, what rooms might be bookable and so on and so on, it changes a lot. But if you look at the background knowledge and look at the core data of the regions and so on, that doesn't change so much. If an event is coming up, then the event comes up, but is not dead after 1 hour or something like that. So it makes sense to add this to the data store and of course make use of that. So that's an attribute of the region, or might be an attribute of the region or something else, and that's also very popular. Many people search for something like that. But in addition, you have to think about all these different attributes that are currently not available. It's not, right now, it's not possible with any travel business search engine to search for something close to an actual beach. You need these kind of attributes annotated, and that's because there's no data set available. But if we looked at link geodata, for example, which is OpenStreetMap in a typified form, then we have this data available. But it's not easy to include this data, for example, in this case, because that's one case we are working in the GeoNo project on. We have so many polygons representing different kinds of beaches, which makes it quite hard to make a query about that. And that's why we are working on performance, because if we can answer the question, but the user is not ready to wait for this, then it doesn't make sense to include this information.
Thank you.
Okay, a final question. Do you have any impressions how this what is the impact of this optimization with more than 16 million triples?
Yeah, and that's why I said that these are preliminary results, because we are currently working on the whole hotel data set. We would like to extend this whole data set by a factor of 10 to represent something like a retail use case, because there are way more products than hotels available on the world, and so we will. I assume we can show that there are very early results that show that the performance can still be robust if you increase the number of entities.
Yeah, nice. Thank you very much.